Okay, so let's get started with week 9 of interactive live sessions for the course on fundamentals of convective heat transfer. The course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras, and like every other week, we shall be solving some problems together. Now, this week has been all about uh, natural convection. So, question 1 is asking us which of the following heat flow situations pertains to natural or free convection. So, so, so this is our main area of interest, free or natural convection. The question is which of the following heat flow situations? There are four options given here. So it's air conditioning installations and nuclear reactors. Or is it option B, flow of water inside condenser tubes? Or is it cooling of internal combustion engine? Or is it cooling of billets in atmosphere? So among these four options, which of these, in which of these, free or natural convection becomes more important? So let's take a look at the solution. It's actually option D, cooling of billets in the atmosphere, because all the other options, the commonality there is that in all of them, uh, forced convection plays a bigger role. Let's take each example. So in air conditioner, we see that there are these fans, right, blowing over, uh, cold air in the indoor unit as well as the hot air in the outdoor unit. In case it's a split air conditioner that we're talking about, or in nuclear reactors, there has to be very precise and very powerful ways of taking away heat from the reacting tubes, because otherwise uh, there might be cases of accidents which we really want to avoid. Then flow of water inside condenser tubes. So here the flow itself is uh, ensured by a pump. So this case also pertains to forced convection way more than natural convection. And cooling of the internal combustion engine. This is again a very crucial cooling application where uh, you know heat is produced in the engine due to chemical reactions with the fuel and the air, and it's used for generating power. But if we do not cool it properly, that might lead to different problems. It might lead to damage of the actual parts of the engine, as well as it could lead to thermal runaway, where the combustion really blows up, and that can be catastrophic as well. So there is a specific coolant which is pumped across multiple areas surrounding the combustion chamber of the engine. There is also very much of a designed and forced convection that goes on. Only while cooling of billets in atmosphere. So billets are a stage where a stage of metal processing where large blocks of metal known as billets, they are allowed to cool in atmosphere, and they are simply kept in the atmosphere and no air is blown or anything about them. They just cool due to natural convection primarily. So the surrounding atmosphere is at a lower temperature than the billets. So TB is much greater than T infinity, and the surrounding air takes away heat from these billets and allows it to cool in a very slow manner, because cooling it rapidly might create some defects within the metal block, and we don't want that. So anyway, so this is the only option or the only heat flow situation where natural convection is more important and not forced convection, right? So that's why option D would be the correct answer. Now let's take a look at question number 2. which is asking us that from the integral solution of natural convection over a vertical plate, what is the ratio of the average Nusselt number? This is what we, this is how we denote the average Nusselt number to the local Nusselt number at y equal to h. So what is the ratio between them? The average over the local Nusselt number. Is it option A 4 by 3? Is it option B 3 by 4? Is it option C 2 by 3? Or is it option D 3 by 2? So let's take a look at the solution. It's actually option A 4 by 3. So if you remember, uh, you know, the Nusselt number depends on HL by K, right? And this in turn depends on delta, and we saw that delta by y, in which we can find from the integral solution, actually leads to the uh, average Nusselt number calculation having an integral of the sort. There will be some constants before, and there will be y to the power minus 1 by 4 dy, and this integral will actually lead you to 4 by 3, because 1 by 1 minus 1 by 4 is equal to 3 by 4, and here we have to divide by it, so ultimately we will get something like this, and there will be C and all that. So this is the uh, ratio between the average Nusselt number to the local Nusselt number at y equal to h. All right. Moving on, we'll move on to question number 3. It is asking us match the similar cases with respect to natural convection over inclined plate. So we have inclined plates and we have different configurations. We could have hot side facing downward, hot side facing upward, cold side facing upward, or cold side facing downward. So basically what I mean is, let me draw them. So I'll draw the hot plates in red, and let me take a different color for the cold plates, maybe blue. So we can have two cold plates like this as well. Now hot, uh, so let me finish this. So this is option 3, this is option 4, and option 3 is cold side facing upward. So this is how it's facing, and it could be cold side facing downward, which is option 4, and to red, this is option 1, hot side facing downward, this is how it is, and hot side facing upward. So this is how this one is. This is option 2. So these are the 4 configurations. Now among them, with respect to natural convection, which of them are exactly the same or the similar? Is it, so pairs of them would be similar. Is it 1 4? Is it and 2 3? Option A. Or is it option B 1 2 and 3 4? Or is it option C 1 3 and 2 4? Or is it option D none of the that none of these are correct? So if you think about it, let's say let's draw the boundary layers. Yeah, so let's take a look at the solution. It's actually 1 3 and 2 4. We will soon look at why that is the case. So let's say if I have a hot plate like this, the plumes will start from the bottom, and the boundary layer will start from the bottom and try to go up, but it won't expand as much because it's actually moving up, because gravity acts in this direction, so the buoyancy will act in this direction, and as a result it actually moves towards the wall. So the boundary layer is not as thick as in the other case. So let's say in this case where the boundary the hot side is facing upward, there we will see that. So in case 2, we will see that the boundary layer forms, and that boundary layer actually tries to go away from the wall. As a result, this thickness is higher. Now comparing the same things with the uh, cold plate. So in case 3, here the surrounding fluid will get cooled by the wall and flow downward. They will become denser and flow downward. So the buoyancy force will also be downward in a cool case. So here we will see uh, boundary layer forming, but once again, since its movement is uh, towards the wall, the boundary layer won't be as thick. Whereas in the other case, just like case 2, we will have a boundary layer thickening way more because now the force is acting away from the wall, and the fluid will also try to move away from the wall. So if you look at the shapes of the boundary layers, these two are similar, 1 and 3, and these two are similar, 2 and 4. So which is why option C would be the correct answer. Okay. So moving on, we'll move on to question number 4 now, which is asking us that between two cases undergoing natural convection, sorry, between two cases undergoing natural convection, which one would have a higher Nusselt number? Is it option 1? So once again, just like the previous question, we are clubbing together the similar cases. So hot side facing downward and cold side facing upward are basically the same fluid dynamics wise. So that is option 1, and option 2 is hot side facing upward or cold side facing downward. That's also, these two are the same, but among 1 and 2, which one would have a higher Nusselt number? So NU1 and NU2, which one would be higher and why? You can unmute and answer, or you can type in the chat box as you feel comfortable. And if you have any doubts regarding any question or whatsoever, feel free to ask. So let me draw the situation here. Uh, I'll draw the hot plates in both cases. So case 1 is like this, where I have a hot plate and it's facing downward, and case 2, where again I have a hot plate but it's facing upward. So what happens is due to this temperature, there will be some natural convection currents being set up. So here this wall will heat up and the flow will try to happen upwards. So it will basically go this way, another streamline will go this way, like this. It will try to bypass it. Whereas in this case also it tries to flow up. So maybe it will flow up this way, and then again cool air will come down from above and convection currents like this will be set up. So among these two cases, in which case do you think the Nusselt number will be higher or the heat transfer rate will be higher? In case 1 or case 2? Case 2, correct. So that is the correct solution, and the reason is that these convection currents like this, they actually take away a lot of the heat very easily, whereas in case 1 the flow itself is obstructed by the wall, so that doesn't really facilitate natural convection much. And similar things, just the reverse of them, happen when we take cold side facing upward or cold side facing downward. I hope that part is clear. Okay, good. So moving on, we'll move on to question number 5 now, which is asking us that for natural convection over a hot sphere, where is the maximum value of H? Then different values of the angle theta is given. So if I have a hot sphere like this, which is at a higher temperature than its ambient, and from the center, let's say if I'm measuring theta, I call this theta from the bottom. So bottom most position is theta equal to 0 degree. Then I have different options. I have theta equal to 45 degree, theta equals 90 degree, then theta equals 180 degree. These are the options. So this is option A, this is option B, then C is 45 degrees. So this is option C, and 90 degrees is option D. So among A, B, C, D, where do you think the value of the local uh, convection coefficient H would be maximum? And this is a hot sphere, so the plume forming will be moving upwards like this. So this is how the natural convection plume forms around a sphere and is moving upward. So where do you think the value of H would be maximum? Is it option A, theta equal to 0 degree? Is it option B, theta equal to 180 degree? Is it option C, theta equal to 45? Or option D, theta equal to 90 degree? So as it turns out, H actually depends on the temperature difference. So sorry. So as it turns out, this follows something like this: equal to K, then dou T dou R, and this dou T dou R actually depends on the temperature difference, which is constant here, divided by the boundary layer thickness. So less the thickness, more would be H. Where do you think in this picture this delta is minimum, or the boundary layer thickness is minimum? For what value of theta? This is the boundary layer thickness. So what's your guess? Option A, option B, or option D? Which one should be the correct answer? So as you can see from the figure, the delta is minimum at this location, at theta equal to 0. So there is a huge temperature difference between uh, the surface of the hot sphere and the surrounding fluid within this region. So that's where there will be a huge temperature gradient, which will lead to a high value of H as well. So the correct answer should be theta equal to 0, option A. Let's take a look at the solution, and it is indeed the solution. Any questions on this? I'll go back, take a look at the picture, and let me know if you have any questions. Okay, so let's move on. We'll move on to question number 6 now, which is a numerical type question. It's telling us to consider a hot horizontal cylinder at 60 degrees Celsius of length L, of length 1 meter, diameter 0.2 meter, placed in a cold liquid at 10 degrees Celsius. Now we have to calculate the rate of heat loss, basically Q. That's what we have to find. Now, Prandtl number of the liquid is given, so is the conductivity. Now, it's taken that take Rayleigh number for this particular flow condition as Rayleigh equals 10 power 6. So, what will be the heat loss rate of heat loss? So, we already have this, you know, expression given by Churchill and Chu, which we are using for horizontal cylinders placed in liquid. So Rayleigh number in our case is given. We will simply plug that value in. We have zero point 0.6 plus 0.387 into Rayleigh number powers 1/6. So this is basically 10 power 6 to the power 1 by 6. So this actually becomes 1. And in denominator I have this thing 0.559 by Prandtl number. So Prandtl number value is also 0.559. So this becomes 1. 1 power 9 by 16 is also 1. And this whole thing powers 8 by 27. And this whole thing square. So I'm moving over here. So Nusselt number I have 0.6 plus 0.387 divided by, so this is 1, this cancels off, so basically I get, and 1 to the power 9 by 16 is also 1, so I have 1 plus 1 power 8 by 27, so basically 2 to the power 8 by 27. And this whole thing is squared. So let me just quickly calculate this. uh, So I want 2 powers 8 divided by 27. That is something like 1.228. This is 1.228. So now I'll take the ratio 0.387 divided by 1.228. That gives me 0.315. I'll add zero point 0.6 to it and then take a square of this. So finally, Nusselt number is coming out to be 0.83, 837. Okay, and now, okay, so for Q, I need HA delta T. Delta T I know, A I can calculate from the geometry, H needs to be found out, and this is the Nusselt number with respect to diameter. So Nusselt number with respect to diameter is HD by K, which is equal to 0.837. Now H will be K by D into 0.837. K I know to be 0.025. D is zero point 0.2 into 0.837. I'll simply plug these numbers in and get H. So multiply this with 0.025 and divide it with zero point 0.2, I get h equal to 0.1, 0.105. Okay, so I'll just plug all these values in. I have 0.105. Area is basically, so area is pi r is the circumference, 2 pi r is the circumference into, uh, or I won't write r, I'll just use a equals to pi d into L. So pi into d is zero point 0.2 into L is 1. So basically I have zero point 0.2 into pi. I'll do all that. So let's just plug it in here. Pi into zero point 0.2, that's area. Then the temperature difference is 10 degrees Celsius and 60 degrees Celsius. So it's 50. Finally, what I get Q to be equal to is, let me calculate this now. So 105, pi, I have zero point 0.2, and I have got 50. The product of all that is close to 3.28. 3.28 watts. So that's the answer. Yeah, so that's how you approach problems like these. Now moving on to question number 7, which is telling us that by integral solution of natural convection over a flat plate, the velocity profile is given like this. Now you have to find the location of the maximum velocity. So how would you do this? You know the uh, expression of v. So for maximum, you simply have to take the derivative of that to be 0, right? So basically, this tells me that v equal to v naught into x by delta 1 minus x by delta squared. So for maximum, I have to set dou v dou x is equal to 0. What does that give me? That gives me v naught, and okay, so this we will expand out. I have v naught into x by delta minus 2x by delta squared plus x by delta cubed. If I differentiate it now with respect to x, I get 1 by delta minus 2 into 2 would give me 4. So 4x plus 3 into x squared by delta cubed. This is what I'll get. And this will have to be set to 0. Now let me multiply this entire thing by delta cubed. Then what I'll get is, and v naught I can remove. So I'll be left with 3x squared minus 4x into delta plus delta squared is equal to 0. Now this simply becomes a factorization problem which can be solved like this. So I can have, I can split this middle term as minus 3x delta minus x delta. So I can take 3x common and minus delta common from there, and here I'll have x minus delta equals 0. So x has two solutions at delta and at delta by 3. So this x equal to delta solution is doesn't make sense because let's say this is my velocity profile, right? So I have v by v naught, and let's say I have x by delta over here. So at 1 or x equal to delta, this boundary layer anyway, the velocity anyway becomes 0. So that won't be the location of maximum velocity. Maximum velocity would be in this location at 1/3. So x equal to delta by 3 is the correct answer. Alright, so that's all for today. Thank you.